Okay, so now we're going to take a look at a more in-depth approach to understanding our linear approximations and then see how does it tie with this chapter title of differentials. What are those? Okay, so what I have here is I have a graph of basically what our goal is that let's say, for instance, we have this point C, and I'm trying to figure out, and I know this, I'm trying to figure out what is this value equal to. So what is this y value? Now, using our linear approximations, we said maybe this is difficult to find, but if I draw the tangent line at this point here, so let's draw the tangent line here, I could now use my tangent line and say, oh, I don't know this, but evaluating a number into a tangent or into a line is very easy to do. So this point right here, this is going to have some y value that comes from the equation of our tangent line. So if you remember this tangent line, this is going to say that our y value here was going to be f of c plus f prime of c times x minus c. But in this case, we know what our x value is. We're evaluating c plus delta x. This is what we're plugging in for x. So this becomes f of c plus f prime of c. And then this value, our c plus delta x minus c, goes in there. So the c and the negative c are going to cancel. So this y value is f of c plus f prime of c times our delta x. So this is truly what the y value is of our approximation. This is our f of c plus f prime of c times delta x. So this is our approximation. This is our exact value. Now, when it comes to distances between some of these, this distance, the distance from c to c plus delta x, well, you've just added a delta x, so this distance is delta x. Now, what we'll assume over here is that the distance between these two values, this was the change in x, this distance here we're going to say is our delta y. So that is this distance between these two values. Now, we obviously, maybe I should draw that a little bit lower here. We obviously don't know exactly what this value is, right? If we knew what this value was, well, then we wouldn't need to do the approximation. But instead, what we have is we do have this difference instead that is going to be the best that we can do to approximate our delta y. So the distance between these two, well, this distance, obviously, we can subtract these two values, and what we end up getting is just f of c times delta x. So this, our evaluated difference in y values is the following. We're going to have f of c plus f prime of c times delta x minus our f of c. Or in other words, this is the same thing as f prime of c delta x. So this quantity, f prime of c times delta x, this is going to be as good as we can get to approximate our delta y. So this, now, as a note here, when it comes to mathematical approximations, we assume that we know this distance. We don't assume that we're ever approximating something with x's. We imagine that all of our errors, all of our approximations come from not knowing our y values. So we assume that we know delta x, but delta y we're trying to approximate. So now, just as some notation now and some definitions, is that we often, instead of using delta x, we're going to write dx instead. When we move on into chapter 4 and we start doing integrals, we're going to see dx all the time. But this idea is this distance between these x's. Dx is going to be used instead of our delta x often. Now, this is called the differential of x. Now, you might be thinking, well, then, is dy the same thing as delta y? Well, not quite. So our definition here is that if we have y as the function f of x, the differential of y, dy, this is going to be found by this. dy is going to be f prime of x times dx. So notice in this case, dy is not going to be the same thing as delta y. It's going to be an approximation. And so over here, we notice that we said our delta y this is what we'd like to know, but instead we found f prime of c delta x. So because c was the specific point, if we just generalize that to our x, we get this idea that delta y is kind of like dy, but we could calculate what this dy is. dy is this distance. And so this is our differential of y. So then calculating differentials is very easy. So if we look at, say, an example, if we have y is equal to, say, 4x squared, then our differential, so if we calculate our differential, well, our dy is just found by taking the derivative, 8x, and then we throw in a dx over there. So this is the differential of y. The differential of y is simply found by taking the derivative, plugging it in, and we have our dx there. So I think hopefully when you see this example, many of the other examples are going to be very similar. You're basically just using this definition of putting the derivative, but then you have your dx at the end.